Hi, everyone. I'm Angela Zhou. I just started as an assistant professor at USC Marshall in data sciences and operations. It's great to be here today and hear about all these cross-cutting issues in a variety of different domains. I'm going to be talking about algorithms as instruments, optimal encouragement designs, with a case study on supervised release. So I'm going to start from a kind of broad overview of the problem setup, specialize a little bit to the case study, and focus on talking about the methodology at a very bird's eye level. So I think often about algorithmic decision support and so-called consequential domains. A lot of work in algorithmic fairness also focuses or considers these consequential domains broadly defined. And so in these settings, we ultimately have some kind of really important consequential outcome. Why? So in criminal justice, which is the case study I'm going to be specializing to, you may want to predict at the time of arrest whether or not an individual will appear or reappear for their court date. In financial services, you may want to understand who is going to pay or repay or not repay a loan. In social services, you may want to understand who is going to remain permanently housed after you give them temporary support versus who will not be. And given the importance of these outcomes, there's a lot of interest in developing predictive models based on some kind of information about individuals, covariates, in order to understand or triage resources appropriately. And so that leads to the rise of these predictive models. I'm going to call them, broadly speaking, algorithmic recommendations in R. So these are predictive models, and they're often summarized into, for example, binary categorizations, such as this person is high risk or low risk, trying to classify a person or classify this outcome of interest. Now, on the other hand, given the central importance of these outcomes, there's also a lot of interest in these domains in additional beneficial interventions to try to improve the probability of beneficial outcomes. So this idea of a treatment is that we want to direct resources to try to ensure that people do in fact experience the beneficial outcome. And so this project is specifically about trying to disentangle the impacts of algorithmic recommendations for treatment from the actual impact of receiving treatment themselves. And this is particularly important because in consequential domains, we typically require that important decisions about life chances are made with some kind of clinical judgment or a human in the loop. So there are a lot of reasons for this: procedural transparency, as well as information asymmetry. So when there's a human in the loop, these predictive models, this algorithm decision support, can often simply be an instrument into receiving treatment. But on the other hand, the main causal structure here is that algorithms affect who receives treatment, but they themselves don't affect the outcome. So predictive models don't affect the outcome. So when does this kind of disentanglement matter? It matters if we have separate preferences, for example, on the disparities in treatment and outcome, because typical algorithmic auditing focuses on auditing the recommendations themselves, or thinking about recommendations as treatments. So the previous picture often considers recommendations to be equivalent to treatments, or that recommendations impose the treatment. But in settings where there's substantial heterogeneity in who receives treatment based on clinical judgment, our preferences or our policy relevant considerations may in fact be different in these two stages. So I'll just specialize this a little bit to the case of supervised release. So pretrial risk assessment has been considered a lot in algorithmic fairness. The decision support tool that I'm going to be focusing on is on supervised release. So supervised release is an intervention that's been of recent interest. The outcome is failure to appear. And the causal impact here is whether someone fails to appear when they receive or when they are subjected to electronic monitoring or supervised release. So typically in this problem, people have been released either unconditionally or detained pretrial. Pretrial detention is of course extremely costly. Supervised release is an intermediate intervention level where you release with some kind of conditions, or you ask them to participate in supportive services. It's becoming more popular as an option because pretrial detention is so extreme. On the other hand, evidence is extraordinarily mixed as to its efficacy. It's very heterogeneous, and there are essentially decision support tools out there in the wild that recommend supervised release based on predictive models. But to my understanding, no one in the community knows how these recommendations were determined. So there's opportunity to improve these algorithmic recommendations in a data-driven way. Just to provide some descriptive evidence that there's substantial heterogeneity in these two stages, both in the causal effects and in who gets assigned electronic monitoring based on the recommendations. Here are some distributions from Chicago. So the left-hand column is an estimate of the treatment effect. The top left is the distribution of causal effects for males versus females. Unfortunately, in the data, it's only recorded in this binary fashion. That's fairly common in the criminal justice system. And the main point is that treatment effects are heterogeneous. So actually, there are some subpopulations where this treatment or this intervention would actually increase your probability of failing to appear. So by instead tailoring algorithmic recommendations, we can improve causal effects for the population. On the bottom is breaking down these distributions instead by recorded race. Now on the right-hand column, we're showing the distributions of the lifts in probabilities of receiving the intervention when it is recommended or not. And so again, this essentially demonstrates substantial heterogeneity in who receives the treatment on the grounds of the algorithmic recommendation itself. So because there's a substantial heterogeneity and we have different preferences on, for example, who receives treatment versus our kind of aggregate interest in the population welfare, this has implications for how we think about optimal or constrained optimal policies in this case. So the goal of the methodology is to develop an algorithmic decision rule that can be personalized based on this information, this covariate information that recommends release to optimize the population expected value. So our objective function is going to be some balancing of costs and benefits. Now in the unconstrained setting, unsurprisingly, this will depend on a cost weighting based on both the heterogeneous causal effect and the difference in treatment. We can also think about policy relevant considerations. So there's a lot of concern from advocacy groups about supervised release. There's a lot of concerns because electronic monitoring is of course surveillance, and then we saw disparities in essentially who receives surveillance. So you may be concerned about either parity in beneficial resources or reducing disparities of burdensome surveillance. And so you can add these as constraints to such an optimal policy learning problem. I won't go into too much detail. You can characterize the solution to this fairness constrained program. It's going to be group specific thresholds in the causal effects, but your choice of threshold is going to depend on this lift in treatment probabilities given the recommendations. So I won't go into detail about methodological extensions. There's a lot of other things you can do. You can improve estimation quality statistically, and to handle a lot of the complexities of real world data, you can use robustness to provide sensitivity checks for all of these challenges. So the most important one here is that algorithmic recommendations are of course non-randomized, but now that we've disentangled these two stages, we can use robustness to be robust to in extrapolating one of these stages, but not both of these stages at the same time. So I'll wrap up there. I've mostly described just at a high level, but I think there's a lot of important opportunities for really kind of characterizing to what extent does this human in loop matter in a lot of different domains. Thank you.